You know, in the world of chemistry, there's this one family of compounds that has a seriously split personality. On one hand, they are absolute life-saving heroes, but on the other, they're some of the most notorious environmental villains we've ever created. So today, we're going to dive into the wild story of haloalkanes and haloarenes.
I mean, just look at chloramphenicol. This is a chlorine-containing compound, and it's actually made by microorganisms in the soil. It's an incredibly powerful antibiotic that's been a game-changer for treating things like typhoid fever. A total chemical hero, right?
And then you've got something like halothane, which is a synthetic halogen compound. For decades, this was the go-to anesthetic for surgery. It made countless modern medical procedures not just possible, but painless. So another big win for the good guys.
But then there's the other side of the coin, the villains. I'm talking about freons. You've probably heard of them as CFCs. They were celebrated as miracle refrigerants. They were stable, non-toxic, perfect for your fridge and your AC. That is, until we figured out they were literally tearing a hole in the Earth's ozone layer.
So what is it? What gives this family of molecules this incredible power for both good and, well, evil? Okay, let's get into it, because it all boils down to a single, super important chemical bond.
Pretty much everything about them, how they react, how stable they are, their role in making other chemicals, even their environmental impact, it's all dictated by the bond between a carbon atom and a halogen atom. Chemists have a shorthand for this. They just call it the CX bond.
And it all starts with this thing called polarity. You see, halogens, think fluorine, chlorine, bromine, they're really electron hungry. They pull the shared electrons in the bond closer to themselves, which leaves the carbon atom a little bit electron poor with a slight positive charge. This makes that carbon a super attractive target for other molecules, and that's what really sets the stage for all the chemical action.
Okay, but here's where it gets kind of counterintuitive. You might think that the most polar bond, which is carbon-fluorine, would be the most reactive. But nope, it's actually the strongest bond of the bunch and the hardest to break. The real action, the most reactive bond, is actually the weakest one, carbon-iodine. So here's the key takeaway. It's the bond strength, not just the polarity, that really tells you how reactive it's going to be.
All right, so this brings us to the first major character in our story, the haloalkanes. These are the molecules where the halogen is attached to a simple chain of carbon atoms. And just like their bond strength suggests, these guys are generally super eager to react.
So what do? Well, their go-to move is a reaction called nucleophilic substitution. It's basically a chemical swap meet where an electron-rich molecule comes in, attacks the carbon, and kicks the halogen out. But here's the thing. They don't just do it in one way. They can take two very different paths to get to the finish line. And we call these the SN1 and SN2 mechanisms. Think of it as two different roads to the same place, and each road has its own set of rules.
Okay, let's break these two paths down. The SN2 path is a direct one-step deal. The new molecule attacks at the exact same time the halogen is leaving. It's all one synchronized move. It's like a perfectly coordinated dance. The SN1 path, though, that's a two-step process. First, the halogen just leaves on its own. This creates a really reactive, positively charged carbon thing called a carbocation. And only after that does the new group come in and attack. This tiny difference in timing, well, it changes everything.
And this quote just perfectly captures what happens in that one-step SN2 attack. Because the new group has to attack from the back, from the side opposite the halogen, the molecule's whole 3D shape literally flips inside out. It's called a Walden inversion. And that image of an umbrella in the wind, that's exactly what this molecular somersault is like. The SN1 reaction, totally different outcome. Remember that flat, positively charged carbocation that forms in the middle? Well, since it's flat, the incoming molecule can attack it from the top or from the bottom with a totally equal chance. So what do you get? A perfect 50-50 mix of both the left-handed and right-handed versions of the product. And we call this process racemization.
Okay, now let's meet the other side of the family, the haloarenes. In these molecules, the halogen is attached directly to an aromatic ring, like a benzene ring. And unlike their super reactive cousins, these molecules are famously, stubbornly unreactive. So, the big question is, why? Why this dramatic shift in personality? Why does hooking a halogen onto a ring instead of a chain suddenly make it so unwilling to do those substitution reactions we were just talking about?
Well, the answer isn't just one thing. It's actually a trifecta of stabilizing factors.
It's a combination of something called resonance, the type of carbon atom the halogen is attached to, and just how unstable the intermediate products would be. Let's break that down.
So if you remember one thing, remember this: resonance. The electron pairs on the halogen atom don't just sit there. They actually get shared around the whole aromatic ring. And this sharing creates what we call a partial double bond between the carbon and the halogen. A double bond is way stronger and shorter than a single bond, which makes it incredibly hard to break.
So what we have here is one character that's eager to react and another that's super stable. Now this isn't a flaw, it's actually a feature. Chemists have learned how to use these different properties, turning haloalkanes and haloarenes into one of the most versatile tools for building other, way more complex molecules.
Just look at this. You can start with a simple haloalkane, and just by picking the right chemical to react it with, you can create a whole bunch of different types of molecules. Want an alcohol? Bam! Use potassium hydroxide. Need an ether? No problem. Use sodium alkoxide. They're pretty much the ultimate starting point for making all sorts of things.
So what about those stubborn Haloarenes? Well, unreactive doesn't mean impossible. If you're willing to use some serious muscle, I'm talking cranking the temperature up to 623 Kelvin and the pressure up to 300 atmospheres, you can force them to react. This is actually a huge industrial method called the Dow's process, and it's used to make phenol.
And that brings us right back to where we started. We've seen the chemistry that makes these compounds so incredibly useful, but that exact same chemistry is what's responsible for their complicated legacy as both saviors and destroyers.
Seriously, the Family album is just full of these double-edged swords. You have chloroform, a pioneering anesthetic that can also break down into a deadly poison gas. Freons kept our food cold, but they wrecked the ozone layer. And DDT, it saved millions from malaria and won a Nobel Prize before we realized how toxic it was to the environment and had to ban it.
And these dangers are not just some abstract idea. They have very real consequences. Let's go back to chloroform. If you breathe in air that has just 900 parts per million of it, that's less than 0.1%, it's enough to make you dizzy, tired, and give you a headache. It just goes to show how razor-thin the line can be between a useful tool and a dangerous poison.
So, the whole story of haloalkanes and haloarenes really leaves us with this massive question for the future. We get the chemistry now. We know how to harness their power. But as we keep designing and making brand new molecules, how do we get better at seeing the long-term consequences? How do we make sure that our next miracle compound doesn't become the next generation's biggest villain?